So, chapter 4, music. Well, look, I didn't know anything about music whatsoever, but I stumbled across this numbering for the standard tuning, which is 440 hertz on the A note of the middle octave. And the international standard is currently set at 440 hertz. But this wasn't always the case. And so what I did was to look at the Mod 9 results for the frequencies of each of the notes, and I discovered that in fact there was a repeating sequence every 6 octaves. So every 72 notes it repeated. So for example, the octave 6 above the middle goes 3 6 9 6 6, and then you'll see that the middle octave goes 3 6 9 6 6, so they're 6 apart. And what we take away from that is that there are 5 sections of the octave that are 1 2 4 8 7 5. There are 4 sections that are 3 and 6, and there are 3 sections that are 9 or 0. So there's the 72 number sequence in music. So what I did, rather like we did for the multiplication tables and the individual numbers to see how they're paired and mirrored, I did the same thing for each of the octaves. And lo and behold, the octaves are paired and mirrored and separated by 3 octaves. So you get the octave 1 below going in a clockwise direction and then an anti-clockwise direction, and they're mirrored. They're paired and mirrored. And each of the 3 octaves have a mirroring octave. So then I discovered that the international standard of tuning wasn't always the preferred standard. And in fact, if we go back a long way, we go back to something called the Pythagorean musical scale. And instead of it being 440 on the A of middle C, it's set at 432. When scanning Mod 9 across the numbers produced by that particular tuning, I found something really quite interesting, because this time there are only 2 sections that have 1 2 4 8 7 5 versus 5 in the 440 tuning. There are only 2 sections that are 3 and 6 versus 4 using the 440 tuning. And there are 8 sections that are 9 versus only 3 using the 440 hertz tuning. And again, there's the 72 number sequence, and again we see the pairing and the mirroring of the octaves, separated by 3 octaves. So then what I did was to plot the entire 72 number sequence for 440 on the circle to deliver that picture. And then I displayed the same for the 432. Look how beautiful and smooth and beautiful and flowing that one feels versus this one. And what I'm saying is that there is electromagnetic interference in the 440 tuning that disallows this more direct, uninterrupted relationship with source. Bach and Mozart used this standard, the 432. And perhaps that's why their music is imbued with a certain special something. It's certainly my feeling when I listen to that. That is the feeling that I get. There's something else that is just truly beautiful. When we look at the journey of these number pairs from the smallest to the largest, so starting with 0 0 and then 0 9 and then 1 8 and then 2 and 7, then 3 6 4 5 5 4 6 3 7 2 8 1 9 0 9 9. When we consider what do we have to do to make the journey up, so to go from 9 to 18 we have to double it, which is the octave. To go from 18 to 27 is multiplying by 3 over 2, which is the perfect fifth. 27 to 36 is 4 over 3, which is the perfect fourth. And on, and we get all of the major tones. And unbelievably, when we look at 9 is to 8 relative to 10 is to 9, we get the ratio 81 is to 80, which is the syntonic comma. Now, 81 is a particularly interesting number because 80 divided by 81 gives you 0.987654321. And 1 over 81 gives you 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what I call the music of the decimal system.